Deuterium is one of two stable isotopes of hydrogen. The nucleus of deuterium, called a deuteron, contains one proton and one neutron, whereas the far more common hydrogen isotope, protium, has no neutron in the nucleus. Deuterium has a natural abundance in Earth's oceans of about 1 atom in 700364200000000006420 of hydrogen. Thus deuterium accounts for approximately 0.0156% of all the naturally occurring hydrogen in the oceans, while the most common isotope accounts for more than 99.98%. The abundance of deuterium changes slightly from one kind of natural water to another. The deuterium isotope's name is formed from the Greek deuteris, meaning second, to denote the two particles composing the nucleus. Deuterium was discovered and named in 1931 by Harold Urey, earning him a Nobel Prize in 1934. This was followed by the discovery of the neutron in 1932, which made the nuclear structure of deuterium obvious. Soon after deuterium's discovery, Urey and others produced samples of heavy water, in which the deuterium had been highly concentrated. Deuterium is destroyed in the interiors of stars faster than it is produced. Other natural processes are thought to produce only an insignificant amount of deuterium. Theoretically, nearly all deuterium found in nature was produced in the Big Bang 13.8 billion years ago. As the basic or primordial ratio of hydrogen 1 to deuterium has its origin from that time. This is the ratio found in the gas giant planets, such as Jupiter. However, other astronomical bodies are found to have different ratios of deuterium to hydrogen-1. This is thought to be as a result of natural isotope separation processes that occur from solar heating of ices in comets. Like the water cycle in Earth's weather, such heating processes may enrich deuterium with respect to protium. The analysis of deuterium-protium ratios in comets found results very similar to the mean ratio in Earth's oceans. This reinforces theories that much of Earth's ocean water is of cometary origin. This figure is the highest yet measured in a comet. Deuterium-protium ratios thus continue to be an active topic of research in both astronomy and climatology. Differences between deuterium and common hydrogen. Chemical symbol deuterium is frequently represented by the chemical symbol D. Since it is an isotope of hydrogen with mass number 2, it is also represented by 2H. IUPAC allows both D and 2H, although 2H is preferred. A distinct chemical symbol is used for convenience because of the isotope's common use in various scientific processes. Also, its large mass difference with protium confers non-negligible chemical dissimilarities with protium-containing compounds, whereas the isotope weight ratios within other chemical elements are largely insignificant in this regard. Spectroscopy and quantum mechanics. The energy levels of electrons in atoms depend on the reduced mass of the system of electron and nucleus. For the hydrogen atom, the role of reduced mass is most simply seen in the Bohr model of the atom, where the reduced mass appears in a simple calculation of the Rydberg constant and Rydberg equation. But the reduced mass also appears in the Schrödinger equation, and the Dirac equation for calculating atomic energy levels. The reduced mass of the system in these equations is close to the mass of a single electron, but differs from it by a small amount, about equal to the ratio of mass of the electron to the atomic nucleus. For hydrogen, this amount is about 1837-1836, or 1.000545, and for deuterium it is even smaller, 3671-3670ths, or 1.002725. The energies of spectroscopic lines for deuterium and light hydrogen therefore differ by the ratios of these two numbers, which is 1.000272. The wavelengths of all deuterium spectroscopic lines are shorter than the corresponding lines of light hydrogen, by a factor of 1.000272. In astronomical observation, this corresponds to a blue Doppler shift of 0.000272 times the speed of light, or 81.6 km per second. The differences are much more pronounced in vibrational spectroscopy such as infrared spectroscopy and Raman spectroscopy, and in rotational spectra such as microwave spectroscopy because the reduced mass of the deuterium is markedly higher than that of protium. Deuterium. A Big Bang nucleosynthesis. Deuterium is thought to have played an important role in setting the number and ratios of the elements that were formed in the Big Bang, combining thermodynamics and the changes brought about by cosmic expansion. One can calculate the fraction of protons and neutrons based on the temperature at the point that the universe cooled enough to allow formation of nuclei. This calculation indicates 7 protons for every neutron at the beginning of nucleogenesis, a ratio that would remain stable even after nucleogenesis was over. This fraction was in favor of protons initially, primarily because the lower mass of the proton favored their production. As the universe expanded, it cooled. Free neutrons and protons are less stable than helium nuclei, and the protons and neutrons had a strong energetic reason to form helium-4. However, forming helium-4 requires the intermediate step of forming deuterium. Through much of the few minutes after the Big Bang during which nucleosynthesis could have occurred, the temperature was high enough that the mean energy per particle was greater than the binding energy of weakly bound deuterium. Therefore, any deuterium that was formed was immediately destroyed. This situation is known as the Deuterium Bottleneck. The bottleneck delayed formation of any helium-4 until the universe became cool enough to form deuterium. At this point, there was a sudden burst of element formation. However, very shortly thereafter, at 20 minutes after the Big Bang, the universe became too cool for any further nuclear fusion and nucleosynthesis to occur. At this point, the elemental abundances were nearly fixed, with the only change as some of the radioactive products of Big Bang nucleosynthesis decay. The deuterium bottleneck in the formation of helium, together with the lack of stable ways for helium to combine with hydrogen or with itself, meant that insignificant carbon, or any elements heavier than carbon, formed in the Big Bang. These elements thus required formation in stars. At the same time, the failure of much nucleogenesis during the Big Bang ensured that there would be plenty of hydrogen in the later universe available to form long-lived stars, such as our Sun. Abundance deuterium occurs in trace amounts naturally as deuterium gas, written 2H2 or D2. But most natural occurrence in the universe is bonded with a typical Un-H atom, a gas called hydrogen deuteride. The existence of deuterium on Earth, elsewhere in the solar system, and in the spectra of stars, is also an important datum in cosmology. Gamma radiation from ordinary nuclear fusion dissociates deuterium into protons and neutrons, and there are no known natural processes other than the Big Bang nucleosynthesis, which might have produced deuterium at anything close to the observed natural abundance of deuterium. There is thought to be little deuterium in the interior of the Sun and other stars, as at temperatures their nuclear fusion reactions that consume deuterium happen much faster than the proton-proton reaction that creates deuterium. However, deuterium persists in the outer solar atmosphere at roughly the same concentration as in Jupiter, and this has probably been unchanged since the origin of the solar system. The natural abundance of deuterium seems to be a very similar fraction of hydrogen, wherever hydrogen is found, unless there are obvious processes at work that concentrate it. The existence of deuterium at a low but constant primordial fraction in all hydrogen is another one of the arguments in favor of the Big Bang theory, over the steady-state theory of the universe. The observed ratios of hydrogen to helium to deuterium in the universe are difficult to explain except with a Big Bang model. It is estimated that the abundances of deuterium have not evolved significantly since their production about 7017435494880000000 13.8 BYA. Measurements of Milky Way galactic deuterium from ultraviolet spectral analysis show a ratio of as much as 23 atoms of deuterium per million hydrogen atoms in undisturbed gas clouds, which is only 15% below the WMAP estimated primordial ratio of about 27 atoms per million from the Big Bang. This has been interpreted to mean that less deuterium has been destroyed in star formation in our galaxy than expected. Or perhaps deuterium has been replenished by a large infall of primordial hydrogen from outside the galaxy. In space a few hundred light-years from the Sun, deuterium abundance is only 15 atoms per million. But this value is presumably influenced by differential adsorption of deuterium onto carbon dust grains in interstellar space. ISO-SWS observations find 22 atoms per million hydrogen atoms in Jupiter, and this abundance is thought to represent close to the primordial solar system ratio. This is about 17% of the terrestrial deuterium to hydrogen ratio of 156 deuterium atoms per million hydrogen atoms. Cometary bodies such as Comet Hale-Bopp and Halley's Comet have been measured to contain relatively more deuterium ratios which are enriched with respect to the presumed protosolar nebula ratio, probably due to heating, and which are similar to the ratios found in Earth seawater. The recent measurement of deuterium amounts of 161 atoms d per million hydrogen in Comet 103P Hartley, a ratio almost exactly that in Earth's oceans, emphasizes the theory that Earth's surface water may be largely comet-derived. Most recently the deuterium-protium ratio of 67P Churyumov-Gerasimenko as measured by Rosetta is about 3 times that of Earth water, a figure that is high. This has caused renewed interest in suggestions that Earth's water may be partly of asteroidal origin. Deuterium has also observed to be concentrated over the mean solar abundance in other terrestrial planets, in particular Mars and Venus. Production deuterium is produced for industrial, scientific and military purposes, by starting with ordinary water, a small fraction of which is naturally occurring heavy water, and then separating out the heavy water by the Girdler, sulfide process, distillation, or other methods. In theory, deuterium for heavy water could be created in a nuclear reactor, but separation from ordinary water is the cheapest bulk production process. The world's leading supplier of deuterium was Atomic Energy of Canada Limited, in Canada, until 1997, when the last heavy water plant was shut down. Canada uses heavy water as a neutron moderator for the operation of the CANDU reactor design.